Hello, and welcome to this multi-part series on GPU computing and parallel computing. Now, in this session, we'll be looking at an introduction to GPUs and see how we can use GPUs for parallel computing. So let's get started. My name is André Brodgaard, and I'm an associate professor at the Oslo Metropolitan University. Okay, so in this session, we'll be looking at two things. First of all, parallel algorithm design, sort of classify what kinds of algorithms do what kinds of things, and then programming of GPUs. Start off with the first one. If we look at parallel processing, we, in the previous session, looked at different types of processors and saw that we could have a set of multi-core CPUs where you have identical processing units across, so each core is identical to the next one. But then you could also have different processors, which is kind of like the heterogeneous computing mindset, where you have a multi-core CPU and a GPU coupled together. Now, the benefit of the symmetric multiprocessing, which is the multi-core CPU, and that's that the tasks take the same amount of time, whichever core it runs on, more or less. If you disregard non-uniform memory access, that's a true statement. Now, memories, all of the memory can also be seen by all processors. Now, if you look at the heterogeneous computing, you see that it's slightly different. If you look at the previous session, we saw that multi-core CPUs had their memory space, which is RAM, and the GPUs had its other memory space, which was the GPU memory. So that means that each processor only sees part of the memory, and furthermore, each processor runs the different tasks at different speeds. Now, we can mix these above and use message passing and these kinds of things and make it as advanced as we want ourselves. But we're not going to go there first. We're going to start off a bit easier first. Now, most algorithms are like baking recipes, and they're often designed for a single person or a single processor. So it's like a baking recipe where you have first do A, then do B, continue with C, and finally complete by doing D. Now, how can we do things like utilizing an army of identical chefs, right? And how can we utilize an army of different chefs? These are the kinds of questions we should be having in the back of our minds. The army of identical chefs, that corresponds to the multi-core setting, the symmetric multiprocessing, and the army of different chefs, that's the heterogeneous computing setting. So, if we look at, that's the types of architectures, more or less. But if we look at the data loads, we can see that we can structure things into different types of parallel algorithms. And one type of parallel algorithm is the data parallel algorithm, which is very often used because it's very easy to get started with. Now, data parallelism performs the same operation for a set of different input data. So this matches very well with our single instruction multiple data set, which we discussed in the previous session. So a vectorized instruction would work very well for this. And this scales very well with the problem size. So the larger problem you have, the more processors you can utilize. And one example here is the vectorized multiplication of two vectors. So element-wise, that is. So if you do A multiplied by B, and these are vectors of 1,000 elements each, you can do things like shown here. C of I is equal to A of I plus B of I. And you see that every element I in this, so element 0, 1, 2, 3, 4, goes to different processing units. And then you get your 1,000 elements done in one clock cycle instead of 1,000 clock cycles if you use a parallel computer with 1,000 processing units. Now, that's if we disregard the memory issue. We'll come back to that later, but let's assume that's true for now. Okay, so that's the data parallel workload. Another type of workload is the task parallel workload. And in task parallel workloads, you typically divide a problem into subtasks that need to be solved individually. So here we have one example where we have 4 processors and processor 1 renders a user interface. Processor 2 simulates some physics, processor 3 calculates some statistics, and processor 4 writes some statistics to disk. Now, if you think about this, the most computationally demanding part here is often things like simulating the physics or calculating the statistics. And that means that rendering the user interface on processor 1 is just using a small section of what the processor is actually capable of. So here we're just using, we're not using the full potential of our computer. Now here is another way of doing task parallel workloads, and that's pipelining dependent operations. So you pipeline this into the following example, where you first read some data on processor 1, you compute some statistics on processor 2, write some statistics and write some data. And by doing that, you're able to overlap more of the operations. So you see that as we go along, more and more processors are actually working simultaneously. But there is an issue. All of these gray sections here are still wasted clock cycles. So you still are not utilizing the full potential, and you're typically limited by the most expensive parts. So computing statistics and processing statistics is the things that are limiting our performance in this example. Now, a third way of doing this is to do an analysis of all the operations you want to do. And instead of pipelining them, as shown in the previous example, you create a directed acyclic graph of the operations and schedule the operation as soon as it is possible to run it. And by doing that, you can remove a huge part of the wasted time, which is shown here in this example from Jack Dongarra from a paper back in 2012. So that reduces the spare time that the computers are just idling. Okay, so these are some ways of thinking about parallel computing, right? And things we can think about when we're designing algorithms. But often if you speak with people and they don't know too much about parallel computing, they think of supercomputers as a million CPUs, which runs 1 million times as fast as your single CPU. And unfortunately, that's not true. Now, in theory, it does exactly that. It runs like 1 million times faster with 1 million cores. But the problem is that you're not going to get 1 million times speed up. So let's look at Amdahl's law. Now, any algorithm you have will have a serial section, a part which you cannot parallelize. That means reading something from disk, writing something to disk, or some initialization or so on. And these cost. So even though you have a parallel section of your code, and you make that part of your code run infinitely fast, that's not going to do anything with the serial section of your code. And if we look at this graph here, this graph up there, right? That graph up there, that shows something like the 95% graph, this one up here, which is the green one. It shows that if you have a computer code which is 95% parallel, the highest speed up you're going to get is 20 times. That sounds kind of bad, right? Because 95% parallel, that's essentially all parallel code, but it's only going to get 20% faster, even though you're using 1,000 cores or 1 million cores. Now, the reason for this is that you cannot do anything about the 5%. So if you have your computer, your algorithm takes this long, right? And the 5% is this small section over here. Now, what you do with your super fast computer is that you're removing all of your parallel sections, so that takes 0 time, but it doesn't change the serial section. So the most you'll get is a 20 times speed up. That's essentially Amdahl's law. Now, that's kind of pessimistic. So let's look at a different phrasing of this, and that's called Gustafson's law. And what Gustafson's law essentially says is that if you have a problem which is 95% parallel, make sure that your parallel section, sort of this section over here, is much larger than your serial section. So move solve a bigger problem, right? If you solve a bigger problem, you're going to make your parallel section much longer. And by making your parallel section much longer, you'll be able to get a higher speed up. So that's essentially Gustafson's law, which is more optimistic. And this sounds perhaps like cheating, but often it's not, because what you can do is you can solve more accurate physics, you can solve more physics, and you can solve with a higher spatial resolution and these kinds of things. So by doing more work, you're going to get more accurate results in the same amount of wall clock time. And now back to one of the pet peeves I have. Now, if you look at today's computers, the major bottleneck for our computing is moving data. And this example always makes me have a bit of a guilty conscience, because downloading 1 gigabyte from Japan to Switzerland consumes roughly the energy of 1 charcoal briquette. And then when I think about all the YouTube videos I've streamed and all of the Ubuntu images I've downloaded and so on, it becomes quite a lot of energy. And essentially, if you look at today's CPUs, a single floating point operation, a flop, costs less than moving 1 byte. So moving data into your chip is more expensive than working with it on your chip. So the key insight here is that flops are for free, but moving data is expensive. And flops, floating point operations, that's your plus, minus, multiply, divide, these kinds of things. Think of those operations as free, and think about moving data as expensive. We'll come back to this later on, but let's see how bad this actually is. Now, if you have a single precision number, and you're looking at the optimal ratio of how many operations you have to do with this when you bring it into your GPU or your CPU, it's quite devastating, right? So for each single precision number you read into your GPU, you should perform over 60 operations with it. So if you do A plus B is equal to C, that's 1 operation. You're getting A and B and you're storing C, and you're doing a single operation. So that means that operation is extremely bound by memory bandwidth. So it doesn't help you to have a faster CPU. It's the memory that's the bottleneck of your computation. And on CPUs, it's similar. So it's been growing over the last years. So memory movement is a huge issue for computing, essentially. Now, this is often called so-called memory-bound applications, which are bound by the memory bandwidth. And this is, for example, matrix multiplication. Matrix multiplication is a whole lot of computations, but it's still bound by memory movement. And compute bound, that's, for example, computing pi. We'll see that in a later example in this video series. Now, a third limiting factor here is actually the time spent waiting for data, the latencies. As I've said previously, waiting for data is quite important on GPUs and CPUs, and waiting for floating point units and waiting for other things that are not available at the time on your processing unit. So, in essence, if you're looking at an algorithm, you have to think about the total algorithm and the total way it works on a processor. You cannot just think about the algorithm itself or the processor by itself. So if you look at this graph sort of illustrates that you have a numerical performance of an algorithm, which essentially tells you how well does your algorithm fit with the processor. So if you have a massively parallel architecture and a massively parallel algorithm, that's a very good fit because it's going to be way up here. Now the problem is that these kinds of algorithms are often very inefficient in an algorithmic sense. So for example, in matrix multiplication, you can do it in an efficient way and in inefficient ways. And the inefficient ways can be up here in terms of algorithmic performance, but in terms of numerical performance, how well they fit with the architecture, they're way up there. So often you find some sort of trade-off. You find an algorithm which is relatively good in terms of convergence speed and these kinds of metrics that also fits quite well with your architecture. So you need to think about both the algorithm and the computer you're working with when you're designing and working with codes. Okay, so let's change pace and talk about programming GPUs. Now, this was when I started working with GPUs. I think it was around 2005 or so. Now, GPUs were back then programmed using OpenGL and graphics languages. And you could see things such as this, where you would have some geometry that you're rendering with a texture of a wall and a flashlight. And by multiplying these, you'll get the flashlight on the wall. And then some clever researchers figured out that you could essentially rephrase things like matrix multiplication to look like these kind of algorithms. So they were using this kind of algorithm to solve matrix multiplication. So this was back in 2001, Larsen and McAllister, which had this very early paper on matrix multiplication on graphics hardware, which was really cool to see. And I did similar things when I first started working with GPUs. Now, this was a nightmare to work with. You had OpenGL drivers, which were buggy, and you had to rephrase everything as if you were working with graphics. You had to trick the GPU into doing mathematics. It was just a nightmare. Since then, we've had a huge improvement. We had the first generation graphics APIs, which people abused and tried to do some GPU computing with. And then you had a set of academic approaches to GPU computing. And I call them academic because they were kind of proof of concept and not really industrial strength. And then in the third generation, you have proper C-based languages, which have good industry support. And today you have NVIDIA CUDA and OpenCL, which are the most promising ones. And what's missing here from this slide is the fourth generation, which is the type of languages that are built on top of this as well, which try to translate Python into GPU code by itself. Numba, for example, which does these kinds of things. So today we have a huge range of tools we can use. And in this course, we're going to be looking at OpenCL and CUDA, which are the basic building blocks for building high performance code on GPUs today. Now, CUDA was released back in 2007, and it enables GPUs to be programmed with a C-like language. It's essentially C or C++ with some additional syntax. We'll look at examples later on. And OpenCL is a very good alternative, very similar, and runs on all other hardware than NVIDIA, essentially. Or it runs on NVIDIA as well, but it runs on all other hardware as well. Now, we're going to be using OpenCL in this course for the exercises, but you'll see that OpenCL does have portable code, so you can run your code on Intel Xeon Phi AIM GPUs and CPUs and NVIDIA GPUs, but the performance will vary quite a bit. So even though you can run your code on multiple architectures, you'll typically write special versions for special hardware as well. Now, built more high level than this are the high level ones, which is the OpenACC, C++ AMP, Numba, and so on. And these work very well for toy problems, but often they have problems with automatically moving data. So by using these, you have to phrase your program carefully so that it looks like what the languages expect. So you cannot do all the tricks that you can with OpenCL and CUDA. Okay, so let's look at a proper example. Let's look at how we can add some matrices in CUDA. We want to add these two matrices up here. So this is A, this is B, and then we do C, which is this one here. So we do the 1 plus 0 is equal to 1. And we do 1 plus 7 is equal to 8, and so on. And on the CPU, we can do it with this function here. Add function CPU, where you have the float C, the float A, and the float B. And you have the size of your matrix. So the float star, if you're not familiar with C or C++, that means a pointer. So it's essentially just the matrix. And then we have to index into this, and then we need the columns and rows to be able to find out how large the matrix is. So we loop over all of the rows and then all of the columns, and then we compute the linear index into our array. So we start numbering this. So it's element 0, 1, 2, 3, 4, 5, right? And we just compute this index k, which is the linear index into your array. And you do that C of k is equal to A of k plus B of k. Very simple, very easy. Now let's look at how we do this in on the GPU. And that looks like this. Okay, so we do have a matrices kernel up here. So it's called a kernel, and kernel just means a function which runs on the GPU. And the way I know it runs on the GPU is because of this special word here, global. By having this global here, I'm telling the CUDA compiler that this function is going to be running on the GPU. As with the CPU function, it takes in the C, A, and B matrices and the size of the matrix. And then finally, we do things like this. We have the X index of our thread, our Y index of our thread, and then we compute the K in this exact same way. Now these X index and Y index, that essentially is related to the parallelism of our code. So our code runs a single thread for every single element of our matrix. So remember our matrix from the previous slide up here. Now we run a single thread for each of them, and our global X and global Y just corresponds to the index of our placement of our specific thread into the matrix. So that's the GPU function. Now to run the GPU function, we have to run it from the CPU. So add function CUDA here, that's a function which runs on the CPU. And what it does is that it creates some parallel structures, a block and grid. We'll come back to that later. Then it moves the data from the CPU to the GPU, because the GPU has to have access to the matrices. And then it calls the kernel. And this means that the kernel now runs with a single thread for every single element in the matrix, which comes back here into the global X and global Y. And finally, once we've run the kernel, we can download the result from the GPU back to the CPU and check our results. And that brings us to the parallelism on GPUs. And on GPUs, it essentially looks something like this. We have a two-layered parallelism. So we have a block, and the block consists of threads. So each thread, that's a single element of your matrix. Think of it as that. Right? So it's an I index and a J index. And by using special slightly advanced GPU techniques, you can collaborate between threads. So this thread over here can share data with this thread over here and this thread. So all of these within a single block can share data, and they can also collaborate a bit because of that. Now, on the other hand, you have your complete compute grid. So this is a block which is 4 by 3 threads, right? And you have multiple blocks such as this. So you have 3 by 2 blocks in your complete domain. So by multiplying this out, you see that you have 3 blocks here, and each block is 4 elements wide, 4 threads wide. So that means that you have 12 threads in your width. So 12 threads in your width. And then in your height dimension, you have 3 threads for every block and 2 blocks. So that means you have 6 threads. So in total, you have 12 in the width and 6 in the height. Okay. Between blocks, you cannot collaborate. So what the GPU does is that it says that, okay, you've divided up your parallel domain, and within each block you can collaborate, but I'm not going to tell you which block I'm running first. So the GPU can actually run this block over here first, and then run this block, and then wait a bit and run this block and this block and this block. So you have no way of collaborating between blocks. So the blocks are independent, but within each block you can collaborate because all of these run at the same time. Another way of viewing this is that you're thinking of each of these as a parallel processor by itself. So you say that this is CPU 0 or GPU 0, GPU 1, GPU 2, GPU 3, GPU 4, GPU 5. So each block has this different GPU. And that's also not too far from the truth because these are scheduled onto GPU cores. So they're actually running most likely on different cores on your GPU. Okay, these threads here shown are in 2 dimensions, but they can be 1 dimension, 2 dimensions, and 3 dimensions. Okay, so communication within a block, that's okay. Communication between blocks, that's not possible. The only way to do that is to run a whole kernel on your whole data set and say that once everyone's finished, we can synchronize and collaborate that way. So that's really expensive and you want to avoid it if you can. Okay, so I've talked about CUDA. We're going to be using that slightly for one example, and OpenCL, which we're going to be using for the programming examples later on. And they're virtually the same. I think I'll skip most of this slide. I can mention the thing that the support for OpenCL is much better. It actually works on the Xeon Phi, NVIDIA GPUs, and AMD GPUs, whilst CUDA only support NVIDIA GPUs. That's the major difference. So often you're going to be using OpenCL if you do not have an NVIDIA GPU, and if you have an NVIDIA GPU, you can use both. But the main difference between them is this. You can essentially do a search replace for CUDA code words and replace them with OpenCL code words and backwards. So you're not supposed to be reading this slide, but it shows that it's more or less a one-to-one correspondence between the CUDA code words and the OpenCL code words. So it's very easy to port between these, and I've done this myself for multiple codes. So this is something which is tedious, boring, but it's definitely possible to do. So let's look at how we do the matrix addition in OpenCL. Now we have, as with CUDA, we have the kernel, which consists of, which takes in the matrix C, A and B, and the width of the domain. And again, you have the global X and the global Y, and these are the location of the thread. This is the location of the thread in the global domain. And we're using this to get the K, which is the index of our element into our matrix. And then actually we do the addition. C of K is equal to A of K plus B of K. And then on the CPU side, it's more of a nightmare, because here you see that we have to set up a lot of kernel arguments. So whilst CUDA has the CUDA compiler, which does more of this, these kinds of things automatically for us, we have to do this manually on OpenCL up until version 1.2 at least. So this is really cumbersome and tiresome if you're doing it from C++ or C. Fortunately, we're going to be using Python in this course, so we're going to bypass all of that. And speaking of Python, Python also works with CUDA. We have PyOpenCL, which we're going to be using in this course, and we also have PyCUDA. And as with OpenCL and CUDA, they're equivalent. The author behind PyOpenCL, Andreas Klockner, is the same as the author between PyCUDA. So it's the same guy writing the abstractions for these two. And here is what it looks like OpenCL through PyCUDA. And here I've shown in using the Jupyter Notebook, where we're using this special magic up here, which says that this cell up here is actually an OpenCL kernel. So this is going to be interpreted as a kernel. And we're seeing that we have the add kernel with the A, B, and C pointers. And then we get the global ID, and we do C of the ID is equal to A of the ID plus B of the ID. So here we just bypass the K, and we say that we're going to be using a single one-dimensional ID here. And to run this from Python, we upload the data to the device, and we call the kernel as a regular Python function. And I think this is extremely nice of using PyOpenCL in the Jupyter Notebook. You get things like this. The add kernel is just a just a Python function which is there available for you. And then you can do things like getting the data back from the GPU very easily. Just enqueuing a copy from your device, which is your GPU, to your host, which is your CPU. Okay. That was a lot of information, but this is still just an introduction, which gives you the overview of things. So we'll go more into detail later on. And what we've looked at in this session is that we've looked at parallel algorithms and how these are divided up into task parallel and data parallel and these kinds of things. And then we also looked specifically into GPU programming and saw that on the GPU, a GPU function is called a kernel. It runs on the GPU, and it uses this massive parallelism to hide the latencies. And remember, we do need to move the data from the CPU to the GPU to be able to use it on the GPU. So that's also an important point. Now, the GPU also uses the block decomposition. So we saw this decomposition of a grid consisting of blocks, and each block consisting of threads. And this way of decomposing the domain exists both in CUDA and OpenCL. And you have the opportunity to do some collaboration, some synchronization within each block, but between blocks, you're not allowed to do anything. Now, if you do this right, you will be able to get something like a 10 times performance improvement. We're going to be looking at an example later on where we see what kind of speed improvement we get when working with this. And typically, if you start off doing this, you get a speed down. So the first GPU program you run, it's going to give you a slower code than your CPU code. But then you need to track down what's going on wrong and then fine-tune it until you get your 10 times speed improvement. Some people claim a 100 times speed improvement, and most of the time those claims are kind of cheating. They're not comparing fairly. So something like 10 times, that's more or less reasonable. Now, getting started with GPU computing is really easy, and I hope all of you will be able to run the virtual images together with this course to get started and run this quite fast. In my development environment, I use Miniconda and use the Jupyter Notebook for Python, and it's very, very efficient. So using Python for developing GPU code is really, really recommended. And that's what we're going to be using in this course as well. Okay. With that, I think I'll end for this session and hope that I'll see you in the next session where we're going to continue the journey into GPU computing.